Question 3 was about halogenalkanes. 3.1, draw the displayed formula. This is where you show all of the bonds and all of the atoms fully written out in such a case here. So 1, 1, 2, 1, 1, 1, 1, 2 trichloro, 1, 2, 2 trifluoroethane. In 3.2 we were asked to think about the damage that 1,1,2 trichloro 1,2,2 trifluoroethane can cause. It's used as a refrigerant, as a coolant. It can damage the ozone layer. Now, with any halogenalkanes, we must write a specific example of what happens in the first stage, this sort of initiation stage of this process, where the halogenalkane, where I've written a structural formula, they seem to like the structural formula AQA exams rather than, say, molecular. And so what happens in the first stage is the molecule breaks down to release this highly reactive chlorine free radical, and then there's the byproduct as well. Notice how it's the chlorine that breaks off due to its weaker bond strength rather than fluorine. And then this is regularly observed, so this is specific and this is regularly observed. The chlorine radical here reacts with ozone, forming oxygen, and then the ClO dot free radical. This intermediate radical can react with another ozone, forming two oxygen molecules, and then reforming a chlorine radical. Now this can go back to the start, and it can act as a catalyst, so that's the role of the chlorine atoms in this process. Next we have which of the coolants would cause least environmental damage. Well, it's linking back to what I said on the previous slide, in that the CF bonds in this molecule here are stronger. The CH bonds are stronger as well. In these other molecules, they have CCl bonds, and so they're weaker. And so the CF bonds break. The CF bonds do not break because they're stronger. CCl bonds do break. So it's advantageous to use this type of molecule, hence B, for as a coolant. Give the UPAC name for compound B in 3.4. Well, we're looking at 1,1,1,2 tetrafluoroethane. We can see there's 3 fluorines on the first carbon and 1 fluorine on the second carbon, so we would name it in that way. Next question was about comparing the boiling point of iodomethane versus fluoromethane. Now what they're asking, really getting you to think about here, the fact that they're comparing forces, intermolecular forces between molecules, which then lead to a higher boiling point of iodomethane and a lower boiling point of CH3F, fluoromethane. Now the first point is really to get across that CH3I has stronger van der Waals intermolecular forces. It's got more electrons. That's the key point about the strength of van der Waals, number of electrons. But it's also asking you to compare. So you need to talk about the fact that CH3F does have a permanent dipole intermolecular force, and because it's a more polar molecule, it would have these stronger PD-PD forces, a comparison of forces. However, the van der Waals intermolecular forces will dominate. They are stronger, hence the high boiling point of CH3I. But both are mentioned, and then there's a final sentence for the third mark. In question 4, we're still on organic chemistry here, and we are looking at tests. So in test 1, we're thinking about pentwanine, a reagent that could be used to identify pentwanine, describe the observation. So bromine water, the classic example, also in GCSE, colour change orange to colourless. Second is carboxylic acid. It's pentanoic acid. Well, it's at a carbonate, but it must be a named carbonate. You can't just say carbonate. So sodium carbonate or sodium hydrogen carbonate, and the observation you should mention is fizzing, effervescence, or bubbles. And then finally, the aldehyde. You don't need to mention all this information at the bottom. It's just for just as a reminder. But Tollen's reagent forms a silver mirror in the presence of an aldehyde, pentanal. That's the functional group of pentanal. And then Fehling's test is an alternative. You don't need to. It's or red precipitate is formed from a blue solution. Now what I've listed here is what happens to toluenes. Aldehyde gets oxidised and the silver ions get reduced, and in this case there's also a reduction of copper.